Could shut everyone up.
All right, we'll get started.
Cool.
All right, everyone, please make your way back to the seats for the final talk of the evening. Please make your way back. Wonderful, I'll keep the intro short. We have Sougoumarane with his talk on Multigres Vitesse Vitesse for Postgres.
Vitesse.
Yeah, we'll give it up for Sugu.
All right. Well, I should thank you all for coming here on this weather, you know. I came all the way from California and I'm like, okay. So that's good. You know, like listening to Manya talk, I was thinking, you know, I don't have background in GPU computing, and I'm thinking when I talk about databases, it's probably how people feel that don't know how databases work. So apologies if I missed some of you. Okay, so how many of you have heard of Multigres? Okay, quite a few. How many of you know how databases work? Okay. We're going to have fun. Okay, so what is Multigres? Multigres is Postgres, basically. In other words, Multigres, the goal of Multigres is to make Postgres run better, Postgres run well. How many of you know Postgres? Okay, all right, so all of you have heard of Postgres. So why Multigres? Why are we, Postgres runs it, no, Postgres runs, people use it. So what are we doing Multigres? Why does Multigres exist? So I'll cover a little bit of that. Basically, Postgres was not popular 5 years ago. It suddenly became very popular. And to run databases, you need good tooling. And tooling is catching up. And Multigres is one of our efforts to basically build that tooling for Postgres. Some of you might have heard Multigres is Vitesse for Postgres, or a sharding system for Postgres. They are all true. The whole idea is databases as they stand today don't scale forever. After some time, they saturate the machine that they run on. After that, you are stuck. There is no more scaling you can do. Multigres intends to solve that problem. That is its North Star main goal. But that is not its only goal. The goal of Multigres is to solve other problems also along the way. So, a little bit about our team. We are about a team of about 12 people now, is it? 12 people growing to 15. We have some philosophies, some things that we run. So these are some of the things that we tell ourselves, you know. One thing is Postgres doesn't run itself. You know. If you think that, you know, once you install Postgres, you can just keep running it, it's not going to happen. As you start to scale, start to add more use cases and stuff, you're going to realize that you need actually, you know, an army of people to, you know, keep that thing up. So that is one thing that one problem that we want to solve with Multigres. But then the one thing that we noticed is with in the Postgres world is Postgres has some weird quirks, weird behaviors, and over time people have just accepted them. You know, you know, this replication lag is something you have to live with. Oh, this replication slot, it's a nightmare, but you know, there's no other way out. So there are things like that, you know. So what we came and said was, let us not accept any of these problems that people think are accepted. You know. Let's rethink, see if we can solve all of them. And the other thing is, when you run Postgres, there's a lot of tooling. You bring all these tooling together. And these tools don't really know about each other. They don't talk to each other, but they need to, right? Next goal is to make sure that, you know, everything is well connected. And essentially what we're doing is, the whole idea is when you want to run Postgres, you run it with Multigres. And Multigres is going to do such an awesome job that you won't ever leave Multigres. So that is our goal, It's a one-way street. Okay. So I'm going to be talking about I'm going to throw a bunch of awesome concepts that we use in Multigres. Because you're all technical people, so I'm not going to give the spiel about all the great features that Multigres has. You can actually look it up. It's basically, once you get Multigres and Postgres together, you can essentially scale forever. You can scale to petabytes of data, no problems. That's kind of the goal of Multigres. But what I'm going to talk about is go one level deeper and talk about the cool technologies that we have built or are building underneath Multigres, to get you interested. I actually see Multigres as having three pillars. There's only three foundational pillars in Multigres, and everything else is in one of those three things. The beauty of it is how those three things work together well. The first thing is cluster management. What is cluster management? It directly talks to the fact that Postgres doesn't run itself. So in other words, when you start running Postgres under Multigres, it will take care of all the pain points for you. You have to do backups, you have to do restores, you bring up replicas, you do all those things in a database. All those things Multigres will take care of for you. The other thing obviously is sharding, which means that when you exceed the size of one machine, we make sure that you can split your database into smaller parts and continue to scale. The last one is actually the most underrated problem in the world, which is migrations. And I will talk about that. But before I talk about that, I will give you with one thought, which is the most powerful construct for migration is a select. Keep that thought, I'll come back to it. Okay, in cluster management, what are the cool things that we do in cluster management? Actually, before we go into the cool things into cluster management, I want to prep you with what are the pieces in Multigres? How does Multigres run Postgres? So this is basically how a cluster is born. On the orange, you see that is the only thing that exists. It's called the provisioner. So when you want to bring up when you say, I want to create a database, right? You cannot tell a database to create itself because it doesn't exist. Something has to exist first. That is called the provisioner. The provisioner is something that you run, bring it up once, and then it is there. And whenever you want to create a database, you tell the provisioner, I want to create a database. So when you say create a database, then it is going to spin up a bunch of components. At the bottommost layer is Postgres with that small elephant that you see. And above that Postgres, it has two components called the multi-pooler, and the other one is called the multi-gateway. Why would you want two components when you could have one? Or why would you even want any components at all? So we'll talk about that. How many of you have run Postgres? Have used Postgres? Yeah. So in case you haven't used Postgres before, the first problem that you encounter with Postgres is after a while, it will refuse your connections. You try to connect to it, it says, no, you cannot connect with me anymore because you've used all your maximum connections. So the first problem we solve with the multi-pooler is to basically say, accept all the connections that come in, but multiplex them with the limited number of connections that Postgres has. So that is problem number one that multi-pooler solves. Above that is multi-gateway. The problem that multi-gateway solves is accepting user connections. The multi-gateway scales horizontally. You can have as many as you like. So you could have 100,000 connections, no problem. And they'll all get funneled into these 100 connections that Postgres has, depending on whoever sends a query, it reserves a connection, uses it, and then returns the results. So this is kind of the very simple. So why did we split multi-pooler and multi-gateway into two? It is very simple. The reason is because you start running Postgres, you start with one Postgres, but eventually you will need many, because what if that Postgres goes down? You have to continue serving traffic, so you need a replica or a standby. So when this goes down, your traffic has to move to a standby. That part is handled by multi-gateway. That layer then redirects traffic to the standby. So that is the reason why we have to. There are many other reasons, but I'm trying to simplify things because I saw many of you are not very familiar with databases. So apologies for those of you who already know what I'm talking about. So in this case, once these two are there, the application sends traffic to multi-gateway, and multi-gateway sends it to multipolar. So this looks simple. I'll do a small deviation here about modeless connection pooling. So the one problem with Postgres is if you start a transaction, you have to stick to that connection. Yeah, you say begin transaction, and I'm going to send you a statements, and those statements have to go to that, stay on that connection, and after a while, when you're done, you say commit, and then everything gets committed and gets released. The challenge with that is the stickiness, right? The problem with that is you create a connection and then you do these things. You are not supposed to poison that connection because that connection has to be used by somebody else. You cannot say, set a variable and remember it, because you set a variable and remember it, and if that connection is multiplexed, the next time you come in, you get another connection, that connection won't have that variable, right? So because of these reasons, existing connection poolers, they have this thing called transaction mode and session mode. And in this transaction mode, you cannot do things like set variables and things like that, which kind of reduces your lifestyle. You want to be able to use all constructs of Postgres. So that is a problem that we have solved in Multigres, which is, and why is it that existing poolers cannot solve it is because they have to know what query you are sending. When you do a set variable, they have to parse your query and say, oh, you are trying to set a variable, therefore I will reserve a connection for you. Right? So traditional poolers cannot do it, and that's the reason why they separate transaction mode and session mode. What we can do is, because multi-gateway has a full parser, it knows what you're trying to do to your connection, which means that then we can smartly manage these poolers without you worrying about whether you are setting a variable in a transaction or not. So we understand what you're trying to do, the semantics of your operations, and because of that, the pooling code in multi-gateway does not restrict you into transaction or session mode. You can just use it just like you are connected to native Postgres. All right, so this is how a cluster is born. Quick thing about the box on the right, it's called the topo server. That actually is an etcd instance. And the whole concept here is Multigres is a distributed system. It is expected to run tens of thousands of nodes spread across your entire world. Like when we were running Vitess at YouTube, which Multigres is based on, we had about 50,000 nodes that we were running in about 15 data centers. Each primary had 75 replicas, and there were servers in Taiwan, servers in Singapore, all over the world. And Multigres is capable of running a cluster of that size. And when components come up, they need to be able to discover, talk to each other. The topo server is what is used. Whenever a component comes up, it registers itself with the topo server. Anybody that wants to reach that component discusses, oh, you are here. Let me connect to you and send you traffic. So far, so good. Have I lost anyone? Everyone still with me? Okay, awesome. So this is kind of the next level, right? So I talked about multi-pooler and multi-gateway. That's also called the data plane because it serves your data. All your data flows through there. Then let's start and talk about the control plane. The control plane is the part that takes care of your cluster for you. The big component here is called the multi-org or the multi-orchestrator. What does the multi-orchestrator do is, you can see that I've the multi-pooler and Postgres thing, I've scrunched it into smaller boxes so that, so there is a primary which is the green and the replicas are the blue. The multi-org watches all three of them. And if any time the primary goes down, it immediately chooses a replica and says, you are now the primary. And as soon as the multi-org does that, it communicates to the gateway that the primary has changed, and the gateway says, okay, instead of sending traffic to this database, I'll send it to that one. Sounds very simple, but it's extremely complicated, and I'll explain why in a little bit. What else? There's also an admin tool, which is kind of a dashboard, which helps you look at what's going on in the cluster, what are the servers that are running, what is their health, what are they doing, and stuff like that. And you can see a few more lines here is that as soon as there is a primary and there are replicas, You want to use those replicas for some things. Typically, if your software is scaling, you say, okay, let me not load the primary database with our reads. Let me send some of the traffic to our reads. Multi-gateway can handle that for you by load balancing all these things for you. Of course, replicas lag behind, so you should know that what you're reading is eventually consistent, which is acceptable for most loads here. So here I want to, this is a small takeoff here. I don't know how many of you have heard of separation of compute and storage. You've all heard of separation of compute and storage. So separation of compute and storage, in my opinion, is a very bad idea. The reason is because databases are IOPS hungry. What is IOPS? IOPS is when your compute is trying to access storage. And they are also latency sensitive, which means that when you do transactions with the database, when you do reads, they do a lot of quick reads, quick writes. And that is not good if your storage is not close by, right? So, and there are a lot of systems that use it, so that's the reason why I'm a little pained that they are doing this. Like the database person in me, every time I hear that, why are you doing that? So I hereby present a new way of separating compute from storage, a better way, which is these DBs that you see in the bottom, that is your storage. In other words, storage is your storage plus your Postgres. That is your storage. Treat that as a storage unit and split that into smaller parts and scale that. And multi-gateway is your compute. So in other words, you scale your databases through sharding and replication at the bottom. That's how you scale your storage. And you scale your compute by scaling your multi-gateway. This is actually a better way to model separation of compute and storage, because then you can optimize the relationships that exist within a database to live in the same node, which gives you huge advantages. So I'll talk more about that. I won't have time to cover the theory of sharding and stuff, but maybe in another talk. All right. So what is the first thing that, first innovation that we have done? What we have done is, I talked about the multi-arc that performs these failovers. That is actually a non-trivial problem to solve. And if you go back to it and try to solve it really, really correctly, the only way to solve it is to use what is known as a consensus protocol. How many of you have heard of consensus protocols? All of you have heard of consensus protocols. Okay. So Leslie Lamport came up with this algorithm. And for the longest time, it was unknown until 9/11 happened. And 9/11 happened and everybody said, oh my God, trusting data to be on disk is not good enough for durability. We need data to be elsewhere. So that's when if you look at when consensus became popular, that's when it became popular. And so since then, you say that your data is durable only if it is in a different location. And that is what consensus helps you solve. The original computer science paper came out as saying, a consensus is an algorithm that makes a bunch of nodes agree with each other. Or the way I would like to put it, to make a bunch of nodes not disagree with each other. So you don't want split brain when you try to make a bunch of nodes have the same value. And the great property of that thing can be used in storage when you say accept this value, and then that value is sent to another node, and that node also accepts it. Then that value is considered durable, because even if you lose your current node, it is there elsewhere. So that is what consensus is. But unfortunately, what has happened is that people took this problem definition and found Lamport's implementation of consensus and married the two and said that this is the only way to do consensus, which is a majority-based quorum. That is actually not required. If you look at this statement, if I went to an engineer and said, solve this problem for me, but my durability rules are different, it is solvable, except that they will say, oh, but here's an algorithm already called consensus, the Paxos, which is the protocol, and now the more recent one, which is Raft. So what we have done is we've gone back, restudied this problem from the ground up, and come up with more flexible solutions that are actually more meaningful in the database world. What is a more meaningful solution in the database world? Like, for example, I am an enterprise and I say I want my transactions to be durable. If I write to one node, and if I tell you if this data is on another node on the same rack, will that be enough for you? They'll probably say no, right? It is one other node. Why would they say no? It's what if I lose the rack? Then I've lost all my data. So when you start to ask these detailed questions, they'll have more finer grained requirements. For example, they may say, how about you make sure that my data at least goes to another availability zone? Or if you are now more sensitive, you may say another region, right? Another building. So those are more real constraints that enterprises have. So what we have done is re-implemented consensus to be able to take these types of requirements into account. There is an 11-part blog series that I have written. So if you want more details on that, you may study that. So this is, and in this, the whole idea is that, let's say you started with 3 nodes and then you are scaling, right? You want to be able to add more nodes, right? And without breaking the durability rules. So all those complexities we have handled. All right. The next one is connection pooling. This I've already covered, so I'm going to skip that slide. In sharding. So the art of sharding. What is sharding? Sharding is your ability to break your database into smaller parts. This is something a lot of people have done. There's Cockroach, TiDB, there's Yugabytes. There's so many sharding systems. And they all excel at the art of distributing the data, right? But that is not the true art of sharding. The true art of sharding is the art of co-locating data that needs to be together, right? If you have users and they have transactions, it is very beneficial to make sure that the transactions that the users create live in the same shard as the user, in which case when I create a transaction that involves the user and the transaction, it happens in one shard and it happens in one round trip, boom, done, committed, right? If you do random sharding, then if your rows are not in the same shard, then you have to deal with something called two-phase commit, which is actually 3 round trips at the minimum. And it's not just 3 round trips. You think it is 3 round trips, and then halfway through your coordinator will crash, and then it's like the 3rd round trip didn't happen, so everybody is waiting for that round trip to commit. So if you distribute your data too much, then it doesn't scale really well, and it also doesn't perform really well. So for us to be able to do this, you need actually a sharding model that extends the relational model that exists in database. Now, databases, there is a way where you specify relationships between rows and columns, those foreign keys and things like that. You should be able to extend this into how your data should shard, right? So that actually requires almost a language or a model definition that we have actually defined in Vitess, and using that, a large number of people have successfully sharded, like for example, Slack here. Rafa here is from Slack, and Slack today runs at this awesome speed because of this sharding model. So this is also something that I have covered. All right, migrations. Do you all remember what I said? Select is the most powerful tool for migration. So here is the thing. How many of you have done database migrations? Okay, I want to collect some data. What migration have you done? Like, just name, like, was it Postgres? Was it Postgres versions?
Yeah.
Okay, Postgres versions. Anybody else?
Schema definition migration.
Schema definition, awesome. I got 2 out of 3. One more. Anybody else? Any type of migration that you did? Yes, from one database, one provider to another. Awesome. I think I have all 3 use cases. So all of you, when you did this migration, you wrote your own migration code, right? You had kind of, or scripts, yeah. and you had to basically cobble together things. But You didn't have to. There is actually a way to conceptualize and generalize migration, just like we did the generalization of consensus. There is a way to do it, and the way to do it is through what I call is a select statement. So the way I say it is, anything that you can represent as a select statement can be migrated, kind of. So in other words, you talked about Postgres versions. That's actually select of the whole database. Right? Select this whole database, migrate into something else. Schema migration. That is basically a select statement. Maybe if you're adding a column, add that column to your select statement, right? So if you can basically show a materialization of what your migration would look like, then that is your core component of migration. That's the reason why Rafa and I came up with this name called Multigrep. It's kind of like grep. If there is a file there and you want to extract some things out of that, which tool do you use? You use grep. Use grep and then pipe it to something else, and then you have it. So if you equate select to grep, so anything that you do with grep, you can do with select, except the source is a database. So that's kind of the, and I'll tell you, and now what we have to do, now that you got the concept, what we do is, you express it as a select statement. So you say, let's say I want to migrate, I'll just take one use case. Let's take the use case, take the use case of a schema, right? In schema, I want to add a column. And let's assume that, or let's say, actually, let's do something harder. Let's say, because adding a column, Postgres will do it instantly for you. So then it's too easy. Let's say I want to change this column type from int4 to int8. Right? So that Postgres cannot do. And if your table size is 10 terabytes, it's not going to happen. If you go to the DBA and say, this DDL is not happening, you will live with int4 for the rest of your life. That's the answer you get. So with this, what we do is, you express this as a select statement, except the target is an int8. And what this migration tool will do is, we'll create a shadow table, which is identical to the source, through logical replication, which is basically, it looks at events changing the table and creates this shadow table quietly. But this is something you can do yourself. But what you cannot do is, after this thing is created, that's the place where we have the multi-gateway, right? The multi-gateway is now sending traffic. You can tell multi-gateway, hey, this table is ready to be migrated because it has fully materialized your schema change for you, and it is keeping up. So then multi-gateway will say, okay, stop writes to the source table, wait for the last few transactions to go through, and switch writes to the target table. And boom, your schema is applied. But that's not the end. So what is the biggest risk in migration? The reason why people fear migrations.
Schema drift?
No, not schema drift. Is you migrate and it doesn't work, right? You upgrade your Postgres version and it falls apart. What do? There's no going back, right? So this tool, as soon as you've migrated, will reverse your migration, will reverse replication back to the source table. If for some reason you didn't plan something and it all fell apart, you just go back, revert. So the ability to safely revert back to your old state is actually the reason why most people don't migrate. If you can actually migrate forward, if it doesn't work, you can go back, people will feel a lot more bold about migration. So what have we done in, this is something we have done in Vitess, so we are going to do the same thing in Multigres. We have made this as a core primitive in Multigres, which means that this can be used for any form of migration. Actually, I think I have the list here. So you can migrate to and from Multigres. Like if your database is in RDS and you say, oh, I want to migrate to Multigres, it'll do the thing. It'll migrate your whole database into Multigres. All goes through multi-gateway. And if you don't like it, something went wrong, go back, and go back and forth until you're done. Postgres version upgrades, same thing, reversible. When you want to reshard, it's just a select to the where statement, right? Select where shard key is this, goes to this shard, select where shard key is that, goes to that shard. There is something called, migration can do a lot more than, actually we call it materialization. It can do a lot more than that. You can materialize tables in other places where it will be closer to other shards. What else do we have? Reversible zero downtime schema changes. That is your use case, and a lot more. People have done all kinds of awesome things. This is actually a superpower that we will have, that we believe is going to make people. So the reason is because, like, you write software, and then after a while what happens is, oh, I need to refactor this code because it has grown. You get that freedom when you're writing software. You don't have that freedom with data. Once data is there, it is sitting there, you cannot modify it the way you want it. Like many of you that have worked in databases, if you ask people, if you were to, now that it's been 5 years that you've lived with this data, are you happy with your schema? The answer is almost always no. I wish I could split this table into two. I should have normalized this table long ago. There are things like that. All these migrations you can now do with Multigres. All right. In terms of progress, we are now a full team. We are done with cluster management. It's in alpha on this open source. We'll soon be releasing it in Supabase as a hosted service. And sharding and materialization are coming soon. And that's it for my talk. And thank you for